Hi, thank you. So I'm Carter Wendelk. I'll be talking about how fronto-parietal network reconfiguration supports the development of reasoning ability. So why do we care about reasoning? Well, this is a highly complex ability that allows us to solve novel problems based on prior experience. And it's really a key component of flexible behavior. Now, reasoning ability is really critical for sort of typical intellectual development because it serves as a scaffold for subsequent knowledge acquisition. You need to be able to reason to learn things in school and in life. So reasoning is really critical. And reasoning is an ability that improves throughout childhood, and particularly, so throughout childhood and adolescence, but particularly during the early school years. So there are a variety of different tasks that involve reasoning. For this study, we focused on three standard tasks of reasoning ability, and those are the matrix reasoning task, the concept formation task, and block design. So we treat reasoning ability here as a factor score based on these three tasks. And these three tasks are all very highly correlated and contribute similarly to the overall factor score. So this graph just shows the development of reasoning ability, this RA score in a large sample, a large longitudinal sample that we're looking at, between the ages of 6 and 19. So this shows we see pretty dramatic improvements, large change across this age, and we'll get back into examining this graph a little more later. But this is a basic finding we want to explore the neural basis of this developmental improvement in reasoning ability. So what do we know about reasoning in the brain? Well, there have been lots of studies looking at activation in various reasoning tasks. And so, in general, there's lots of different regions that have been highlighted, shown up as being involved in reasoning. But studies have typically focused or shown particularly that regions within the lateral prefrontal cortex and posterior parietal cortex are especially important for reasoning. And in particular, there's been a whole series of studies that have focused on rostrolateral prefrontal cortex as being really a key region for sort of higher order reasoning tasks. In addition to RLPFC, the IPL, the inferior parietal lobe, is also shown up as being a particularly important region. So I would say, in general, lateral prefrontal and parietal are important, and specifically, or most important, may be RLPFC and IPL. So this shows the network of regions that we think are most important for reasoning tasks. And of course, given the complexity of reasoning as a process and the number of regions that are involved, it stands to reason that interaction among these regions should be really critical for reasoning ability. And so to look at interaction or communication between regions, we can examine functional connectivity. So functional connectivity is just the correlation in fMRI signal time series between regions, and this can reveal interregional interaction. The goals of the current study are to examine age-related changes in functional connectivity within this fronto-parietal reasoning network, and then to test whether and to what extent the changing patterns of connectivity support reasoning at different stages of development. So our participants, our data comes from the Neurodevelopment of Reasoning Ability project. This was a 5-year longitudinal study collected in Sylvia Bunga's lab. The study included multiple measures. We're looking at data from participants that completed fMRI scans and who also completed the several standard tests of reasoning ability. So for the data I'm going to present, we have 132 participants aged 6 to 19. And this is a mixed cross-sectional plus longitudinal design. So lots of cross-sectional data plus a number of longitudinal time. So we have 62 of these participants who have data from time 2. And the average assessment interval was 1.5 years. Okay, so our regions of interest are these lateral prefrontal and parietal regions that I've mentioned. So RLPFC and also dorsolateral VLPFC and ventrolateral or VLPFC within the lateral prefrontal cortex. And also IPL and also SPL in posterior parietal cortex. And so the actual ROIs we used were 8mm spheres based on coordinates from a Power et al. Study, a large-scale intrinsic connectivity study, mapped out different regions that were different in terms of connectivity. So our analysis of functional connectivity involves looking at intrinsic functional connectivity. What this means is the patterns of functional connectivity that are stable across past conditions. These can be very robust patterns, and we think that they reflect within individual history of interaction between regions. So these are maybe a really important indicator of development of actual sort of development of communication between regions. So in order to do this analysis, we formed a number of standard processing steps that are typical of intrinsic functional connectivity analyses. That includes looking just at low-frequency correlation by filtering. And importantly, for our analyses, we had task data. We didn't have resting state data, which is typically used for intrinsic connectivity analysis. We actually had task data, so we moved the task signal, covariate out the task or regressed out the task signal. And also, because there's lots of evidence now that shows that motion in the scanner can have big effects on intrinsic connectivity. It actually removes volumes where motion is detected in order to help control for that. So we did nonlinear modeling of developmental trajectory, and to do that, we chose the cumulative distribution function of the normal distribution as our nonlinear function. And so that has parameters of a mu, which gives a mean age of maximal change, and sigma, which gives a spread of the changes around that mean age. And I'll just show you some examples of functions that could be fit by this nonlinear function, a pattern that could be fit. So if you have a low value of mu, in this case also low value of sigma, we see sort of a sharp change that happens early. That's one possible pattern that we can fit. Intermediate values, we can see a change that happens in the middle of the age range, not so much beginning or end. We can also fit this sort of pattern of a change toward the end. This is also more spread out change. Of course, all variations of these are possible. The basic assumption that this model makes, this function makes, is that changes are monotonic with age. We're not modeling increases followed by decreases. We're assuming that there's going to be sort of one direction of change over this age range. Might not be true for a lifespan study, but it's useful here. And also, this assumes that the age of maximal change is normally distributed. It seems like a reasonable assumption. Because we have, our particular data is sort of mixed cross-sectional and longitudinal, we're using mixed models to analyze this data. So it's sort of an optimal way to combine to analyze this kind of data. So we're basically looking for trajectories accounting for longitudinal change where we have. Okay, so now we return to our graph showing development of reasonability across the sample. And when we apply the model to this data, we get a mu, or a mean age, or sort of age of maximal change of 6 years. So at the very beginning of this age range is where we see that the change is maximal, and a spread of 4 years. So that means that basically in these early ages, from age 6 to 9, 10, we see really rapid change in reasonability. And we can see it sort of slowing down, transitioning in middle childhood, and then really becoming basically adult-like in level, maxing out in the adolescence. Now let's look at what are the age-related changes in connectivity in this network. So ignoring reasoning for the moment. So first we looked at within prefrontal changes, and we saw two strong patterns of change. So one of those was increase between RLPFC and DLPFC. So these two regions are showing a strengthening of their connectivity with increasing age. And the graph on the left shows this pattern. And what's notable here is if we look at the red arrow points to the mu, the age of the maximal change. And we see basically the pattern shows a fairly sharp rise. It sort of transition to adolescence in middle to late childhood. Now, if we look at DLPFC and VLPFC, we see an opposite pattern. So in this case, it was a decrease in connectivity with increasing age. And that shows a transition a little bit earlier, but still sort of middle of childhood, versus the Fronto-parietal. This is a bit more spread out. So this means that there are really different patterns within prefrontal cortex. It's not sort of a general strengthening of prefrontal connectivity or general weakening. It's really a transition of their DLPFC becoming more linked to RLPFC and perhaps less to DLPFC in the pattern of communication. Okay, so now if we look within parietal cortex, we see a weakening of connectivity there. And again, this is happening in the middle childhood where that's the strongest, but also pretty spread out in this case. And then we looked fronto-parietally. The strongest change we saw was between the two regions we care most about or have the strongest hypothesis about in terms of reasoning was RLPFC and IPL, and that was a strengthening of connectivity across the age range. Fairly spread out, but again, concentrated or maximal for the middle childhood at age 12 in this case. So to summarize, for the age-related changes in connectivity within this prefrontal parietal reasoning network, we saw many developmental changes in patterns of connectivity, both increases and decreases. And there were others I didn't show that were weaker. I showed you the strongest ones. And most of the changes in connectivity occur between the ages of 9 and 13. At least the changes are happening most rapidly in that middle childhood age range. Okay, so now we turn to the relationship between connectivity and reasoning. So I show you again our trajectory of reasoning ability. We wanted to look at the relationship between connectivity and reasoning and how it changes with increasing age. So we divided our age range into 3 different groups. And these groups were roughly equal size, and so we have a younger group, a middle group, and an older group. And we could think of, although this is only roughly the case, that the younger group corresponds to the age range over which the changes of reasoning are really rapid or maximal. The middle group corresponds to a sort of transitional period where those changes are slowing down. They're still fairly large change, but becoming more adult-like, or it's a slowing of that pattern. And then the older children and adolescents correspond to an age range where there's fairly limited change in reasoning abilities by this measure. They're looking more adult-like, like young adults. Okay, so first we look at the RLPFC-IPL connection, which was the one that we hypothesized would be most strongly related to reasoning ability. And what we saw was that, indeed, this was strongly related to reasoning ability in the older children and adolescents. But it was not significantly related in the younger groups. And this just shows the scatter plot within the older group. And I should mention that the numbers there are taking into account age also. Okay, so this is the same result, the RLPFC-IPL, and now we also want to look at the RLPFC connection to SPL. So how does that relate? Will that be similar or not? In fact, that shows a very different pattern from the RLPFC-IPL connection. So that was somewhat surprising. We hypothesized that it would be RLPFC-IPL connection most strongly related to reasoning. We thought that SPL might be fairly similar, maybe weaker, not really sure. It was fairly surprising that was actually a dramatically different pattern. And so it looks like it's really the specificity of the RLPFC connection to the parietal cortex that seems to be really relating to reasoning ability. Okay, so now we look at and there were no other effects of fronto-parietal connectivity on reasoning. And now we look at the middle group of children, and here the only significant pattern that we saw was a relation between bilateral RLPFC connectivity and reasoning. Suggesting that maybe it's consolidation of this prefrontal region that we think is really critical for reasoning that has to happen first, and that's more important in this middle age range. And there were no significant effects on reasoning in younger children. No significant effects of connectivity in reasoning. So we have some previous results that have shown that fronto-parietal and even global white matter integrity are related to reasoning ability, but that this relation is almost entirely mediated by processing speed. So we thought here it's important to also look at processing speed to see if that may be a mediator of the effects that we've observed. So that's the last question we'll ask. So we tested a simple structured equation model that includes functional connectivity along with age, processing speed, PS, and reasoning ability. And our basic question was whether or not the connection from connectivity to reasoning ability would survive the inclusion of processing speed. So first, for the result in the older children and adolescents, we saw that indeed that connection does survive. That result is there in the presence of processing speed in the model. And in fact, there was no relation of connectivity to processing speed and no relation of processing speed to reasoning ability. So in this group, the relationship of connectivity and reasoning is not mediated by processing speed. So also for the result from the middle child group, the connection survived inclusion of processing speed. Unlike in the older children, there was a relationship of processing speed to reasoning ability, but there was no relation of functional connectivity and processing speed. So here again, the relationship we observed is not mediated by processing speed. Now in the younger children, we didn't see any significant effects of connectivity on reasoning, but we did see some that were marginal, and so one of the ones the strongest one was VLPFC connectivity, so we included that in the model here. That, of course, still wasn't significant with processing speed in the model, and in fact, processing speed was strongly related to reasoning ability, and it looks like it's sort of a major mediator of the improvement in reasoning over this age range. Major mediator of the age-related improvement in reasoning. So this just to summarize the results I've shown you. For this pattern of change, development of reasoning ability, we saw that RLPFC parietal connectivity, the specificity of the RLPFC parietal connection was the most important predictor or driver of reasoning ability in the older group. Within the younger children, within the middle group, RLPFC connectivity is important, and then processing speed was also important over this age range. Okay, thank you to 20 knowledge people who were involved in this project. Thank
you, Carter. We have time for a few questions.
Hi, that was really great, thank you. So I'm interested in how specific your results are to reasoning ability. Presumably you had a pretty extensive neuropsych battery on your children. Have you looked at whether or not executive function, reading ability, or other measures within mathematical cognition?
Yeah, so first, processing speed was the main one we looked at here carefully, and that was not, I showed you how that was related. We have a mixture of working memory measures, but not the same measure across the entire sample. So those are kind of mixed in the relation. So some of the working memory measure, one does relate to connectivity that's measured we look at here, and another one doesn't. So it wasn't really clear.
Reading?
Reading, we have a measure, and that is highly correlated with the reasoning measure actually, and that's really not as strongly related, but that was also correlated somewhat similarly.
Interesting. And so what do you make of that, if it is related to working memory and reading?
Yeah, so those two measures are so highly correlated. I think it maybe go back to the fact that reasoning is so important for knowledge acquisition. That kind of also reflects your reasoning ability, how well you've acquired that sort of knowledge.
Do you have particular effects that hold regardless of working memory or reading ability?
Regardless, I haven't examined that carefully for all the measures.
Okay, thank you.
Really nice work, thanks. I have a methodological question. Of course, when you are relating brain and behavior, at any point, you really want to make sure that your measures on both sides have relatively high test speed as reliability. As we all know, especially functional data, and especially functional data in younger children, the test speed as reliability is very low. I think that Everett published a nice paper that showed that it's really low, in particular in young children. And you had a unique opportunity here, having longitudinal data, to look at that, and my bet would be, I don't know, have you and what have you seen, both on the behavioral side and the functional side?
Haven't looked at retest reliability exactly in the younger children. I think we do have longitudinal data, but when you get down to like a subgroup like just younger children, the numbers aren't so good to really examine that carefully.
Just to get a feel for it, because my bet is that the values will be all to start with, will be much higher for your behavior, for your assessment of reasoning. I would expect that it will be much higher than your fMRI-based measures. And then on the other hand, they will be higher for the functional-based measures for the older children than younger children. And if that's the case, then the fact that you are not finding any relationship between reasoning ability and the brain data in younger children may be a methodological artifact.
That's entirely possible that lack of finding there. You always worry with younger children. There's lots of issues with it.
Great talk and great data. I'm just kind of curious about your developmental findings and the relational mobility. I'm looking at the tail end where your fixed effects in the model, your group effect sort of levels off and looks like it's flat, but if you actually look at the individual subjects, they all still have positive growth rates. And so I'm curious, like, what do you think of that and the idea that in your whole sample, everybody's continuously improving?
Right, right. What I think about the fact that in the trajectory, I'll go back to the graphs here. And that's, yeah, I think there are improvements going on in that age range, clearly looking at the longitudinal data.
Right, and it's just because it's like, you know, it seems like overall